Okay, so the next and last section that we're going to be looking at is going to be idler gears, okay? Idler gears are found on page 290, kind of the explanation, and it's section 1014. Okay, so let's take a peek at the figure 1022 that focuses here on idler gears, okay? Now, I'm going to tell you the purpose of an idler gear, the sole purpose of an idler gear is to change the direction of the input to the output. That's it. We just add in this extra gear for that purpose only. It changes nothing else. Some students might be like, well, doesn't it change the train value? No, it doesn't. And I'll show you exactly why. But the idler gear in this case, as we go from the input to the output, the idler gear here is number 3. And like I said earlier, and when we calculated our previous example, we put those negatives in front, right? So when we get to the end and we decide, oh, that output RPM isn't what I anticipated or what isn't what I need. Let's say we need to go in the same direction and it calculated to be opposite. We just need to add an idler. Super simple. And the size of the idler does not matter at all. The only thing that's going to matter is if you have some sort of an envelope that you have to work within as far as size. Okay. But whether this is big or small, or whatever number of teeth, it just has to make sure that it can mesh to the same diametral pitch as the 2 gears here. And all it's going to do is it's going to change the direction. Okay. And increase the center distance a little bit. Okay. So let's see how and why it does that. So as we look here, you're going to notice that in this illustration, they've identified gear number 2 as having a pitch diameter of 2 inches. Okay, so on center, pitch diameter, it's going to engage at this point right here with number 3. And gear number 3 has a pitch diameter of 6 inches. So if we look, these two engage, and we would call that, for instance, velocity ratio number 1, right? It would be these first two gears in engagement. Then we're going to look all the way on the other side. We get a second engagement right here, and that's going to be between gear number 3, which is 6 inches in diameter, and gear number 4, which is 8 inches. So we would call this velocity ratio number 2. Okay. Now, if I just do a single velocity ratio between in between number 2 and number 4. So let's say I would go direct from number 2 to number 4, and I would go from 2 inches to 8 inches. What would my velocity ratio be between those two? Okay, so let's just imagine that this idler isn't there. So if I take the velocity ratio and I'm looking at the diameter of number 4 to the diameter of number 2, okay? My velocity ratio from the beginning to the end would be 8 inches divided by 2 inches, right? And my velocity ratio is going to be 4, okay? My velocity ratio from input, number 2, to number 4 is going to be 4. And that would be reasonable, right? That would be reasonable. So if I just take this one out and I go from here to here, this would be 2 inches, this would be 8 inches. A 4-to-1 ratio is not a big deal, okay, to do in one. But remember, if I do them together, the opposite direction of rotation goes from the input to the output, okay? So if I put those together, the input would go, in this case, it shows clockwise, and my output would go opposite, okay? But again, that might be something I'm like, I need those go in the same direction, okay? So I'm going to add an idler. Now, as I said earlier, that idler, its only purpose is to change the direction of the train, okay? So now I'm going to have a train value instead, because I'm going to have 2 pairs of gears in tandem, if you would. So I'm going to have velocity ratio number 1, which is the 2 to 3. And then I'm going to multiply it by velocity ratio number 2. And I'll put my little negatives in front of each one of those. By multiplying those two together, okay, notice that I'm going to end up with a positive value, right? If I just do it direct, this is going to be a negative value because there's only one. Okay, so already you can see that idler is changing the direction for us. But let's make sure that our velocity ratio doesn't change, okay? So let's look at the velocity ratio number 1. So if I look at these two, the two gears that are in mesh are going to be the 6-inch, D3, divided by the 2-inch, which is D2, okay? So this is going to be a negative. I'll put the things in here, D3 over D2, all right? Multiplied by negative, the output is going to be the 8 divided by the 6. Do you see that? So it's going to be 4 divided by 3 here. So it's going to be D4 divided by D3, okay? So if I put my values in, I'm going to have a negative 6 inches, divided by 2 inches. Inches cancel. Multiplied by a negative 8 inches divided by 6 inches. Inches cancel. What else can we cancel?
Negative.
No. Well, the negatives will cancel, right? Because they'll multiply out. Yes, those will. Yeah, we could say that's going to become positive. Okay. But what else can I cancel top to bottom here when I multiply across the top, divide by the bottom?
The
You cancel the
6s.
6s.
I can cancel the 6s. Exactly. We saw a whole bunch of people see that, right? That is our idler. The 6-inch was the idler right here. It was the gear for our first set, and it was the pinion for the second set. Do you see that? Okay. So top to bottom, these went away. So now when I multiply across the top, divide by the bottom, I'm going to get 8 divided by 2. I still get a train value of 4. So velocity ratio is 4 here, but these are going opposite direction because of the negative. Down here, by adding in that idler, I get the same velocity ratio, but this time my input to my output, the direction is going the same. Yes.
You said the idler, the size doesn't necessarily matter.
Correct. Yeah, the size of the idler really doesn't matter. Exactly. Yeah. So if you have, for instance, you're constrained on the center distance, okay, then you just have to, make it appropriate for the size. Now, the thing that is different about center distance here is that you're going to go from the radius of gear number 2. Do you see that? Okay, so if I want to find the center distance from here to here, okay, the total center distance, I'm going to take the radius of the first gear plus the diameter of the idler. The idler diameter will always be in there, okay? Because you would have to do radius and then radius, which is the diameter. Do you see that? And then it's going to be the radius of the last one. So unlike that first set that we did, it was radius, 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 radius. There was no idler in that one, okay? This one, we have the idler, so make sure that when you see an idler, that you take the center distance as a diameter and not as a radius, okay? So for our last example, or our last, if you would, practice problem, we are going to page ahead to page 297, okay? Page 297, and we're going to actually do problem 1053. Okay, problem 1053. And I strategically picked this one because it's using the same illustration as number 52, which you have for a homework problem. Okay, so you'll notice that this is going to be similar, but just different numbers for your homework. So it's a nice example to get done here in class. So here it says we have a gear chain as shown in the figure above. The gears have the following properties. Okay, so our first gear here is number 2. So N2 is 16 teeth with a diametral pitch of 16. And then you'll see the semicolon. And then the diameter of the next gear here is 8 inches. Gears 2 and 3 are in engagement. Okay, so because we have the diametral pitch for N2, it will be the same diametral pitch for gear 3. Then we're going to look at the next set. The next set is number 4, which shares the same center or the same shaft as number 3. So they're on the same shaft. And number 4 has a pitch diameter of 1.5. And then number 5, which it's engaged with, has a number of teeth of 50 and a diametral pitch of 10. Now, as we look across, do you see that number 5 does not have another gear on its shaft? Okay. This is our idler in that set. Do you see that? It's the idler. So now 5 is going to engage with 6, which has a pitch diameter of 5.5. And then D7. So D7, so pitch diameter of 7, not N7, is going to be 1.5 inches. And it has a diametral pitch of 8. And then our last gear here has a diametral pitch of 8 and number of teeth of 56, which is engaged with number 7. Okay, so what we want to find here is we want to determine the velocity of gear 8. So we want to find what is W8 that is driven by number 2, which is going counterclockwise. This is W2 at 1200 RPMs. Okay, so W2 is going counterclockwise. We want to find what is W8 and which way is it going, right? We'll have to know if it's clockwise or counterclockwise. And then also determine that center distance between the input number 2 and the final output number 8. Okay, so the process that we used on our last example is going to be very similar, but we're going to be dealing with an idler this time. Okay, and really the key here is recognizing that center when we do the center distance, that this is a diameter. Okay, so let's go ahead and go through that very same process. Knowing that we have to figure out center distance, we're going to do the diameters for each one of these. So whether it's given or we have to calculate it, we're going to do the diameters for each one of our gears. And that's going to be our, if you would, step number 1. I got to grab some paper. All right. So this is going to be problem 1053. It's on page 297, if you want to add that. Okay. And what we are given is that we have an angular velocity, number 2, that is 1200 RPMs going counterclockwise. Okay, that is our given. And then various items along the way. I'm not going to list all those diameters and numbers of teeth and stuff like that. And what we want to find is we want to find out what is W8 and what is the center distance from 2 to 8. Okay. So what is the output speed of that last gear? And then what is the center distance between the first and the last gear center lines? Okay. So as we had said, we're given, various information along the way. So number 1, we're going to determine all the, pitch diameters, right? Because then it just makes center distance calculations easier. Okay. So we'll start with looking at the problem statement, and we'll notice that for number 2, we're given number of teeth and diametral pitch. So that means that we are going to use that relationship right here to calculate the pitch diameter. So our pitch diameter is lowercase d. We're going to rearrange this to solve for lowercase d using the number of teeth and the diametral pitch. So D2 is going to be equal to N2 divided by the diametral pitch of that gear. So the number of teeth is 16 and the diametral pitch is 16. So 16 teeth, and the diametral pitch is going to be teeth, 16 teeth per inch. The teeth cancel out. So our D2 looks like it's going to be 16 inches. So we'll kind of put our little cloud around there. Go ahead.
Oh, wouldn't it be 1 inch because it's 16 divided by 16?
Yeah, Aiden, that would be it, right? 1 inch sounds actually correct. Thank you. All right, let's see if I can get the next one wrong. So, oh, this one's given. So this one I shouldn't get wrong. So as we look at diameter of pitch diameter for number 3, they're giving it to us as 8 inches. So D3 is going to be equal to 8 inches. So we don't have to calculate that one. All right. And these two are in engagement with one another. Okay. This is going to be our first velocity ratio, number 1, if you would. Okay. Our next gear, as we look here, number 4 is coming forward. It is on the same shaft as number 3. And it's telling us that our pitch diameter of number 4 is 1.5 inches. So that's good. So I'm going to draw just a little line here. And our D4 is 1.5 inches. So that one's given to us, right? So D5, which as we know is our idler, D5 is 50 teeth and a diametral pitch of 10. Okay, so using that same rearrangement that we see here, D5 is going to equal N5 over diametral pitch 5. So number of teeth is 50. And the diametral pitch, it said, was 10. And that's teeth per inch, as we know. Okay. So my D5 is 5 inches. Okay. And then these two are going to be velocity ratio number 2. Okay. Then our next set. Our next set is 5 with 6. Okay. So we already calculated the pitch diameter for 5. So we know that to be 5 inches from above, right? We're just going to list that again. And then it engages with number 6, which is giving us the pitch diameter of 5.5 inches. So D6, 5.5 inches. And this one is going to be our velocity ratio number 3. Does that make sense? So this is our first 3 sets of gears. Notice that number 5 appeared in 2 of the velocity ratios, which we're expecting because we know that that's our idler, right? Okay. Then the last 2, we have 7 coming forward here, and it is engaged with number 8. So 7, pitch diameter number 7, not number of teeth number 7, is 1.5. So D7 equals 1.5 inches. So that's a given. Then we'll probably have to calculate D8. So yeah, it's giving us a diametral pitch of 8 and 56 teeth. Okay. So that means using that same rearrangement as above, D8 is equal to N8 divided by diametral pitch 8. And number of teeth was 56. And the diametral pitch is 8. And that's teeth per inch. So 56 divided by 8, that's 7, right? So D8 is equal to 7 inches. And then this is our velocity ratio number 4. So this time we have 4 velocity ratios to calculate. Okay. So D1 is 1 inch. D2 is 1 inch. D3 is 8 inches. 4 is 1.5. 5 is 5. 6 is 5.5. 7 is 1.5. And 8 is 7. Okay. Now, the next thing we're going to do is we're going to find the overall train value. Okay. And that's going to be multiplying together each one of these velocity ratios. Okay. So our overall train value, so step number 2, train value our overall train value is going to be equal to velocity ratio number 1, put a minus in front of that, minus velocity ratio number 2. So we're going to multiply. It's really not minusing, it's multiplying by the negative version, multiplying by the negative of velocity ratio number 3, and then multiplying by that negative of number 4. Now, we can already see there's an even number here, right? So this is going to be negative times negative positive times negative is negative times negative is positive. So our train value, we can already see, is going to be a positive value, which means that the input to the output are going in the same direction, okay? Now, we need to put the values in each one here, right? So I'm going to calculate my individual velocity ratios back over here. So for set number 1, which was diameters 2 and 3, my velocity ratio 1 is going to be equal to D3 divided by D2, divided by D2, bigger one on top. So that's going to be 8 inches divided by 1 inch. And my velocity ratio number 1 is going to be 8. Okay. Velocity ratio number 2 is going to be the D5 divided by D4. So D5 is 5 inches divided by 1.5 inches. Inches cancel. My velocity ratio number 2. I get for that. What am I going to do? Do you get 3 1/3? Yeah. Velocity ratio number 3 is going to be D6 over D5. So that's going to be 5.5 inches divided by 5 inches. Inches cancel. My velocity ratio number 3 is going to be 1.1. Okay. And then the last one, velocity ratio number 4, is going to be D8 divided by D7. So D8 is 7 inches and D7 is 1.5 inches. But those cancel. Velocity ratio 4 is going to be 4 2/3, 6, 6, 7. Everybody get the same values for those? Okay. Now we're going to take each one of these velocity ratios, put a negative in front of it, and multiply them together to get our overall train value from our input to the output. Okay. So back over here, our train value is going to be a negative 8 times a negative 3.333 times a negative 1.1 times a negative 4.667. So our train value, hope it comes out to be, I don't have the answer in front of me.
I got 136.76.
I'm on my way there. Yep, oops, I got 8.8. Let me try mine again. I got 36.88. Yeah, let's try again. 8 times 4.667 times. Yeah, I get 136.88, 8N. See if you get that same number. Anybody else? A couple people in the room here confirmed 0.88.
I did 2, 3, like 2 decimal points after my 3 instead of 3, I think.
That's
So
probably,
I changed
yeah,
it and that was
hold
it.
an extra. Yeah, okay, excellent. Okay, so this is our train value and it's a positive value. Okay, so that means same direction as input. Okay, so, right. Now, it's asking us for Determine the velocity of gear 8. See, we haven't even done that yet. We've done a lot of calculating already, but we haven't even gotten an answer yet. So number 3 is going to be, what is W8? What is W8? Okay, so we're going to use that train value. We know that the train value is equal to angular velocity of our input to the angular velocity of our output. Our input is gear 2. Our output is gear 8. Okay. Now that we have our train value, we know what our train value is. We know what W2 is. We have to calculate W8. So rearranging this, we would say W8 is going to be equal to W2 divided by our train value. Okay. So we know our input was 1200 RPMs divided by our train value of 136.88. So our angular velocity of 8. You get 8.767. And that would be RPMs. Train value is unitless. RPMs are still on top here. And we know that this was going in a counterclockwise direction, W2. So that means that because it's going in the same direction, positive value up here, then our W8 is going at 8.767 counterclockwise, same as 2. Okay. Any questions on that so far? Got one more thing to calculate, and that's going to be our center distance, okay? So go ahead. I'm confident that you can figure out the center distance. So go ahead and find your center distance. And I'm just going to do one little reminder that, remember, for the distances here from center to center to center to center, remember, you have to take the diameter of the idler. Don't just take the radius of the idler, or do the radius twice if you would, okay? So I get a center distance of 17.25. Did anybody else get that number? Rainer is saying yes.
Yes.
Aiden is saying yes. Okay, excellent. Yeah, and just remembering that that D5 is a diameter, okay? Because of that, because it's that idler. We got to take the whole distance across. Okay. So this is then the last practice problem that you have for module 5. Okay, 17.25, Steve. Okay, excellent, excellent. Okay, I'm going to go back to our PowerPoint presentation, and this should be, we did 53. This concludes chapter 10. So you are ready to get started on the assigned homework here. So just before we look at assignment number 5, let's take a peek at module 5 practice problems. And yes, indeed, we have done each and every one of these now through our lecture/demo. Okay. So you would be ready to hand these in, but don't forget, there are 2 things I want you to identify here. Number 1, just let me know a couple things that you learned, here in module 5. And then I also want you to, instead of telling me what you still are unclear about, that, okay, if you want to share that, I'm happy to take that. But what I want you to do is name 3 places that you see applications of gears in your everyday life. Okay, just look around, see where are you seeing these being used. Okay. So that is module 5 practice problems. Any questions on that at this time? Okay. So then what I'm going to do is I'm going to stop the recording here and then we'll look at assignment number 5.